Welcome back. This is assignment 2A. The problem definition is defined as a function f as defined. It should be defined. It is reprinted incorrectly in the PDF. Let it be. Define a function f as fn equal to fn minus 1 plus fn minus 2. Write a Python program which accepts a value n as input and pass this value to the function. Uh, uh, a suitable error message if the condition for input value is not followed. Okay, so basically, like, the idea here is, like, somebody may request first 5 terms of Fibonacci sequence, or first 7 terms of a Fibonacci sequence, or 11, whatever value. They should not be entering a negative value. That's what they mean here. And the way to calculate a Fibonacci sequence is any value is sum of its two previous terms. Okay, let me run a program before, like, how the output looks like, so that there is no confusion here. Let's say first 11 terms of a Fibonacci sequence. Let's print it. Okay, this is a Fibonacci sequence. For those who have not encountered it in the past, like, 2 is sum of 1 plus 1, 3 is sum of 1 and 2, 8 is sum of 3 and 5, 13 is sum of 5 and 18, 21 is sum of 8 and 13. Okay, 34 is sum of 13 and 21, and so on. So, like, like, anybody can request any number of terms if of Fibonacci sequence, but if negative is entered, negative value is entered, our program should say, like, you have entered a incorrect value, and please enter a positive integer, or some error message like that. Okay, the way it is done is using a mechanism called recursion. In any programming language is function calling itself. Okay, so function calling itself, how it is done is, like, Fibonacci n, whenever somebody calls it, if it is less than 1 or equal to 1, we just return n. Else, like, we call Fibonacci of n minus 1 and Fibonacci of n minus 2. So, okay, so we recursively go on calling Fibonacci sequence till what point? Till a point when we reach n equal to 1, and in which case we return 1. So let's trace this program. Okay, like, let's say somebody passes fourth term of a Fibonacci. Okay, so the way it is done is, like, this is not equal to true. Like, this becomes uh, Fibonacci 3 plus Fibonacci 2. Okay, and 3 in turn gets called here. Okay, then it becomes 2 and 1, and this terminates here. And 2, this we had passed 4, right? So this is 2 and 1. Okay, so we go on summing. So both the left tree and right tree, right, they terminate. When they terminate, when n is equal to 1, so Fibonacci gets calculated recursively. Okay, so Fibonacci value gets calculated recursively. If you need, you can put a print over here, it will become very clear. So the way it is done is, like, we accept input, enter a number of terms in a Fibonacci, we cast it to int, and then from that we come to know how many terms are needed. Let's, in this case, 11 terms are needed. So n terms is 11. Is it less than 0? No. Else, print Fibonacci sequence, and for I in range 11. Okay, I in range 11, that is 0 till 10. Okay, we go on printing n terms of the Fibonacci. Okay, so here this is 5, 5, 10, and 11. So, like, 11 terms you print. So the way it is done is, like, 0 till range 11. So that is 0 till 10. 10 plus 1 0 is, like, 11. So you print 11 terms of Fibonacci. And if you look into this function over here, this function is done using recursion. Recursion, when it terminates when n becomes equal to 1. Okay, although it is n less than or equal to 1, it terminates when n equal to 1. So you trace this program. So I'll be giving it in the resource section. So, like, you run for different values and print the values internally here. Okay, so you will get the idea how the tracing, how the function is working. Okay, now let's move on to section 2b. 2b is for develop a Python program to convert a binary to decimal, octal to hexadecimal using functions. Okay, so the way it is done is we want to convert a binary to decimal value. So no built-in library function is there for this purpose, binary to decimal. Also, we have function for converting decimal to hex. Okay, we have function built-in function for calling from decimal to hex. So octal to hexadecimal, how we do it is first we convert octal to decimal, decimal to hexadecimal. Got it? Octal to decimal, decimal to hexadecimal. So transitively we calculate octal to hexadecimal. The way it is done is we go on extracting individual digits here. So if it is like this, 0 1 0 1 1 1, okay, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 2 to the power 0, 1, 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. So that is what is happening here, pow here, okay, pow. And then we individually fish out the bits the way we were doing in the past also. And then we sum it, okay, we go on summing it. And then in the end, whatever value we would have captured in decimal will be decimal equivalent. So binary decimal equivalent. Here, octal, it is more or less same. Octal, it's more or less same. As you know, in octal, everything will be power of, say, so this is 8 to the power 0, 8 to the power 1, 8 to the power 2, 8 to the power 3, 8 to the power 4. Okay. So that is what is happening here. Okay. That's what is happening here. However, once we get the decimal, we get hex equivalent of that decimal. So this octal gets converted to hex as it is needed here, octal to hex. Okay. Let's run the program. Things will become clear. Okay, let's enter some random binary now value. Let's say 1111. Okay, so this is 15, and then octal value. What value you want to choose? Let's say 567. You should not exceed 8 here. Okay, because it's a octal number system. So this is 111 is 15. Okay, the decimal 15. 567. Let's check using calculator. Okay, so what value we had entered? 567, right? That was in octal. So first you click on this octal. This blue should point to octal. Okay, this is for programmers, programmer calculator 567. Okay, octal 567 is hex 117. So that is printed here. Okay, our program is correct. So we validated the program. So you can this code will also be there in the resources section of download. You can check it. Okay, thank you.